In this couple of lectures, we're going to step back and see some of the more fundamentals theories about machine learning. One of them is PAC learning. So we briefly discussed about it. I think in lecture 3 or 4. On the fourth lecture, I was talking about the Hofting inequality. So that's one of the outcome of the PAC learning, because it defines the complexity for your machine learning models. So let's just have some very rudimentary examples on, being able to use machine learning and how the learning the patterns can be helpful to decide whether or not it's possible to learn at all. So just think about this small training set. So you have a binary training set. So it's a binary classification. Your x's are within binary range, and they are in 3 columns. And your y is the output, either +1 or -1, right? So in our training examples, we have 5 examples. So all 3, 0, the output label becomes +1, right? So 0, 0, 1 becomes -1, and it goes all down to 1, 0, 0, which is -1, right? So given this small training example, can we decide what are these 3 labels are? So say that was your only data set you were accessing to. So using those training set, can we find some information? Can we predict something about the test set? Any guess? So this one, can someone argue whether or not it's +1 or -1? Yeah, as you might have thought, yeah, you can't tell much about this because, first of all, in your training examples, you couldn't find any established patterns about these binary numbers. So these 3 columns, are they representing a number in base 2, or are either separate from each other, either representing other form of patterns? So when you have this 1, you can't gain anything from this training example with the same column having 1. But in this case, you have this 1 as well. So this one wasn't 1. So in this case, the predicted label could be anything. So that's why in this example we can say labels can be anything, as we have not seen them, right? Thus training is not possible in this example. And remember, in machine learning, we don't want to memorize something. We want to find patterns out of data and we apply them outside the training set. So by just looking at these 5 lines of training examples, we can establish any patterns to use it outside in our test set. So that's the reason. Let's have a look at another example. So it's a learning puzzle. So the first row, the outcome of the first row is, So so these two rows are training examples, and the label became -1 in this case. The label became +1. So by looking at the first row, can we find any patterns that relates this become -1 to that pattern? Like say, assume the top left one in a cube in our square that we had, in all three cases is black, right? So one might say, okay, if in our training examples we can find this pattern that maybe if the top left one was black, it's going to result in the true label to be -1, right? So we can predict -1. Or in a second row, can we find any pattern on the second row? Maybe. Can you find any pattern that holds for all these three examples?
Top left again?
Could be, yeah. The top left is always white. One might say that. The other one? Suggestions?
Oh, no, never mind.
Top right?
No, but it's not.
Yeah. Another one maybe? Can you find a similar shape that these three are representing?
Middle right. Middle left.
Mid to right. But how about, so it will hold in these two examples. Well, how about this? Because this one is completely, how about symmetry? How about, can we say these trees are symmetric? That's right, not in the same way. Can we, yeah, can we split them into halves to maybe? You might be able to defer something that these two represent a mirror shape form. Maybe if you divide them like this or this, the bottom half and the lower half could be the same. This one, if you divide it this way, maybe. So in a way, anyway, so now we found these patterns, some patterns. Now, using those patterns, can we predict on the test label here? So can anyone guess what's going to be the outcome of F?
Well, it would depend which one you use. If you just look at the top left, if it's black and white, then you can say it's -1.
That's right.
But if you're using the symmetry, then it's ambiguous.
Exactly. That's exactly why we can say both cases. So it's ambiguous. If you take a look at only the symmetric shape, could be +1. If you take a look at that top left one, could be -1. So given examples we had, no pattern can be found to match a single output, right? So in this case, learning was not possible as well. Now, let's go for a little bit more complex example. I brought this up again on the third lecture, if I'm not wrong. So if you recall, it was a bin of marbles. So you had a bin of marbles that inside that bin you had two different classes or two different set of marbles, red and green, right? And mu was a probability of the red marbles in that bean. Say, so assume mu is 40%. Okay. So since this since this bean consists of only red and blue, so if this one is 40, so we can say green. The probability of green is should be 60, right? Given this example. So now, if we take 10 samples out of this marble and we count the red inside that sample of 10 again, so we're gonna have another fraction, right? In this example, so this example, we became 30%, right? So in this example, the probability of V or nu, the fraction of red marbles in our sample became 30%, right? But we knew that mu inside the bean was 40%. So now, yeah, let's just, so red was mu, green was 1 minus mu, so we define it here maybe as 60% here. And the value of mu is unknown. I just exemplified it by 40% here. So this is unknown. So you don't know this. And we pick several samples. In this case, we pick 10 samples. And the fraction of results, we annotated by nu or v. So can we come up with a solid math or a statistical analysis that how are these two are related to each other, mu and nu? Let me just clear this up. So yeah. So can we find a relation between mu and nu? So does nu or v say anything about our mu when we sample it, or the other way around? So that's the first question. No, as you see, when we sampled here, in this example that you see on the projector, the fractions are different, so the probability are different. But you see they're mostly green, but inside the bean they're not. However, the sample frequency of these two are likely close to each other. So again, take a look at this likely. So we need to take care of this likely first. How likely are they are close to each other? And in what frequency, right? And there's another question, the other way around. What exactly does mu say about nu here? So the first one was yes and no. The second one is what exactly does say. You see that if you carry on sampling from the bean 10 times, 100 times, or if you make the samples large enough with a number n, probably nu, the value of nu becomes closer and closer to nu within a margin, we call it epsilon, right? So in this case, if you assume this was 40%, this is 3 out of 10, so it had like 10% differences. But if you carry on doing this in several samples, or if you take big samples, mostly bigger samples, you might be able to say that they are getting close to each other. So that was the foundation of Hoeffding inequality that we talked about in the lecture 4. We're going to come back to it next lecture. But just to give you some idea about the in-sample and out-of-sample estimations that led to in-sample and out-of-sample error for training examples and test examples. So we use these kind of notations in order to deduce this information. All right, so we come back on Hoeffding inequality next lecture. Now, let's come back to the good old diagram that we started the course with, the learning problem. So now, so far what we've been learning was we had a target function, we wanted to learn, and this one was unknown, because if it was known, there was no need to use machine learning at all, right? So we had a target function, it was unknown. We wanted to learn something from training examples, and we wanted to pair a hypothesis set containing all these h's, so h1, h2, up to hm. So remember, in your perceptron case, this could be any classifier, right? And we wanted to pair this with the learning algorithm A to come up with a final hypothesis. The final hypothesis we chose was G, and it was mimicking the unknown function f that at first we wanted to learn, and we didn't know what it was, right? So for learning algorithm, I made some examples. So you already, we already know several of them, like backprop, hypothesis set could be neural network, right? Or other classifiers. So now, when we have that example in the previous slide, the training examples, we might want to add a probability distribution P on the training examples as well, right? How are we going to pick those examples? What are the probability of different classes inside the training example and outside, right? So this is adding this probability here makes the model more generalized, right? So that you can answer other questions that we want to have when we train a model. If you recall, we were selecting a candidate. So the candidate was from the hypothesis set and paired it with the learning algorithm, and it was the G. All right, now let's talk about a little bit about the hypothesis set and whether or not we can classify them. So are they finite? Are they infinite? So what are they? Let's go back to a binary linear classification. Have you finished writing? Yeah, I can wait here. All right, let's go to the binary linear classification. So in this case, so as an example, learning algorithm could be backprop, hypothesis set of H containing several H's. So these H's could be any classifier. So we pick one of them that we know works the best. In a case of, so it could be neural network in our case, right? And HI, so each of those classifier needs to be a function that maps these two words, right? A DR space to a, because it's a linear classification, so we have either our Y value or either 1 or +1, right? So in general, if we talk about the hypothesis set, this M could be two cases, right? Either it's finite or it's infinite. So let's see some examples about these two cases. Again, these are pretty easy for you now, guys, because you already saw many examples, but this is just for recapping what we've been learning throughout the semester, and then we start going towards the complexity of the problem in a couple of sessions. All right, so in a case of binary linear classification, so as an example, so you have M2, thus you have H1 and H2. Your hypothesis set contains two classifier in this case. H1 is +1, H2 -1, right? So now we can say, given our data set B containing x1, y1 up to xn, yn, so we can output either our candidate, this was the candidate, right? Hypothesis. Either H1 or H2. So we need to pick one of them and use it with the learning algorithm. So pretty straightforward. All right, now see a little bit more juicy example. So we have M as, so in this case 3, 2 dimension. M is 3, thus you have H1, H2, and H3 in your hypothesis set. And these are representing these 3 lines, so think about them as 3 perceptrons. So this is H1, 1 and 1. This area will be classified as pluses, there as minuses. H2 is at 1/2, pluses and minuses, and H3 is intersects with X2 at 2. So on the right side is pluses, the left side is minuses. So you're going to define 3 perceptron case. H1 is assigned x1 plus x2 minus 1. h2 is assigned x2 minus half, and then h3 is x1 minus 2 here, right? So these are your three hypotheses. So each of them are a classifier of its own. So again, given our data set D, x's, the vector of x's, and the labeled y's, so we can output either, again, the candidate could be any of these in a case of a binary linear classification. We don't want to stack them up to make a neural network, but in the case of linear classification, we need to choose one of them that works the best. In this case, M again is finite, right? Okay, so now let's see another example that gives us infinite hypothesis set, right? Or infinite solutions to pick from. Say you have these three data, these two classes, pluses and minuses. So pluses are, and this H3 has effectively classified the two regions. So pluses are on the right side, minuses are on the left side. As you see here, if I drag this H3 a little bit left and right, like here, so I would say H3 prime, or even here, so I'm going to call it H3 double prime, or even more on the right side or on the left side, still I'm able to perfectly classify my region, right? And since this window gives me infinite choices, so the space is infinite. I have infinite number of hypotheses to choose from, and H3 was one of them. So I need to, if I want to have all of the cases, I need to have an exhaustive search for all the numbers, which are definitely impossible, right? So even doing exhaustive search, in perceptron algorithm, we assume all possible linear decision boundaries, right? In this case, we have so many possibilities. Thus, M is infinite, and this property holds in this example. All right, after you saw these trivial examples, we can come back and define the in-sample error or training error that you already been using a lot, and out-of-sample error or test error, right? So going back to the bin of marbles, in general, we take, this was sort of our training example, right? The sample we got out of the bin. So this represents our E-in of edge, and those were outside this sample, inside the bin, or E-out, right? So both nu and mu depend on which hypothesis you choose, and in the learning notation we call this one in-sample error. We define it later in the slides. We call this out-of-sample, right? So E-out. So in a way, in a sense, this represents your training examples that you saw, and these are outside the training example. That's why we call them E-out, because we didn't see them yet. They're outside the training example. All right, so let's define each. It's not readable, right? All right, let's start with the in-sample or training error. So the one here, the one that we saw and we want to train on, right? We want to learn from. Okay, E-in. So in a general way, we can define E-in, and remember this G was the candidate hypothesis that we used in order to train, right? This used to be from the set of edges, big edge, with number of M hypothesis, and the one we chose became G, right? One of them became G. So that's why the function that helps us to learn with the learning algorithm. So E-in of G, in this case, if you want to calculate the in-sample error, it's going to be the summation of all the errors that this G of X, the candidate hypothesis, tries to map the X's from our data set, and we have to, compare them with a true label Y, right? So we have to make a summation of all the errors given the training examples. Compare these two values. So this function, the E y of I and G of xi, is either plus 1 or 0, right? If these two values were not the same, so if this one predicted plus 1 and the true value was minus 1, or the other way around, if it was minus 1 and it turned out that the true value was plus 1, so this becomes 1 and shows that there was an error in the prediction, right? Otherwise, there was no error, so this becomes 0. And in a more condensed manner, we can define an identity function that does the same for you. This is exactly +1 if this were not equal, and it's going to be 0 otherwise. So it turns its identity form. That's why they call it identity function. This one like this, or I. All right, so that's pretty easy. We already know that. In the case of linear regression, then instead of the perceptron, we have regression. In order to calculate the in-sample error, instead of just making a comparison, because in this case these are only +1 or -1, so they're either the same or not. But in the linear regression case, we have to actually deduct these two values. So like the value was here, it was here. So you have this distance to calculate, right? True value. So this gives you a scalar value maybe, or in a higher dimension, it's going to be a vector. So that's our in-sample or training error. We call it E in of G. You've been already using it in your all learning model. Okay, so now let's see the out of sample error. So E out. So E out, we define it by this E shape, the expectation function. So E with this sort of. And we need to consider E out of sample error, or E out, just like the mean of marbles, when x's, the vector of x's, are coming from a probability distribution, right? And this vector of x is independent of those training examples that we train on, right? Think about them. So these were those marbles that we sampled, and these x are the marbles out of sample inside the bean as our test case. Those that we haven't seen them, right? So the classification error for E out would be the probability of the cases that our final candidate hypothesis was not able to classify correctly after we wanted to match with the true label. So it was classifying a green marble where the label was red, or the other way around. Is it clear?
So what's that symbol?
Expectation, they call it. So it's an E with this line here. You've been seeing it in your Gaussian model as well. Yeah. So we define a E out as a probability in this case. Yeah.
The expectation is that the same as expected value, or is that different?
Expected value. So on that case of mu, are you talking about that mean there?
Yeah, expected value is the mean.
Yeah. On that case, the expected value of the x's was the mean, because you were sampling again from something that you as you tested, right? As your empirical data. It wasn't part of your training.
Right.
That's sort of similar, not exactly, but yeah, represent the same shape. All right. So we saw that E out, the test error, is a probability of mismatches between these two. So we can divide this into two. In the case of binary classification, we have two cases, right? The one that these were not equal. So your learning model, your final, your candidate hypothesis on the vector of x was misclassifying it because you understood that it's not matching the y label. And there's another case that it was classifying correctly, right? And we add these two cases together. So that's one case, case 1, and this is case 2. Right? So the overall value is either of this, like the summation of this. Right? The identity value of y, g of x, given the condition that it was a mismatch or prediction error, what we call it misprediction. And it was a correct second case, it was a correct prediction. So if you expand on these two cases, the first case becomes this, that's the second case. Right? When this one is, when you have a correct prediction, this value becomes 0, right? Because there's no error. And multiplying 0 to a probability here makes this whole thing 0. So the only thing that remains is the part for the out of sample error, or E out, is the only part that you do the misprediction, the first section, right? That's why the final value, so this is equal to that, right? So for the out of sample or test, for the test error, we just have to consider the cases that the probability of the cases that the prediction was not correct, and that's all, right? Is it clear? All right. If there are no questions, I'm gonna stop here. And next section, we're gonna come back to that hefting inequality that defines that margin of differences between your mu and nu right? If you recall with that margin of epsilon. And we carry on the pack learning towards VC dimension. All right, so see you guys on Wednesday.